In this video, we're going to derive the what's called the cyclic rule, which is a relationship between three partial derivatives and each other when we have a partial x, partial y, and partial z. So, and then we're going to apply that to the pressure total differential that we developed earlier. dP is partial P partial T times dt plus partial P partial V dV. And we're going to use the fact that beta equals 1 over V partial V partial T, and the constant K equals minus 1 over V partial P to transform this into this. dP equals minus beta over K dt minus 1 over kV dV. So first we need to develop the cyclic rule, and we're going to do that on the next blackboard. So if we look at the total differentials for dx and dy, dx's total differential would be partial x partial y dy plus partial x partial z dz. This is assuming that x is a function of y and z, and all the variables x, y, and z are interrelated through various functions. And then the other total differential dz would be partial z partial x dx plus partial z partial y dy. And so if we solve for or rewrite dz, substituting in this for dx, here's what we get. And then we're going to group together the dy part of this and separately the dz part of this. So let's rewrite it that way. So first we've taken this product and this and grouped them together here. And then we've taken this multiplied by this to get this second term here in dz. Now if we take this term and move it over to the left side, grouping it with this dz, here's what we get. So we have a coefficient times dz equals a coefficient times dy, and since dz and dy are differentials for this function, which are going to vary greatly over the set of input values, the only way for that to be possible, for this relationship to be possible, is if this coefficient equals 0 and this coefficient equals 0. So that gives us that dz or partial z partial x times partial x partial z equals 1. In other words, there's a reciprocal relationship. There's a reciprocal relationship when we're talking about two partials, and this relationship would hold for partial z partial x, partial z partial y, etc. Um, Here's the more important relationship, that partial z partial x partial y equals the negative of partial z partial y, or partial z partial x partial y, and then if we multiply by partial y partial z and move it to the other side, we get partial y partial z equals -1. So this relationship right here is what we call the cyclic rule for partial derivatives. So when there are three partials involved, there is not a reciprocal relationship. Instead of the product equaling 1, the product equals -1. We're going to use the cyclic rule to take the total differential for pressure, this line here, and show that it's equivalent to this other form for dP. And we're going to need to use as intermediaries the fact that beta is equal to 1 over v dv, or partial v partial t, and k is equal to -1 over v partial p. So let's see how we can transform dP into this form right here. So our objective is going to be to transform this form of the dP total differential into another form, and we're going to do that using the cyclic rule. So first, can you verify that the cyclic rule gives us that partial p partial t can be written in this form, minus partial v partial t over minus partial v partial p. You should be able to show that from the cyclic rule, and that's something that we'll work on in class if you aren't able to see how it comes about. So we're going to use these definitions of beta and k to transform this dP, and so let's see how we do that. So first, let's note that we can rewrite this relationship as partial v partial t equals beta v, and so we can put that in the numerator here and write this numerator as minus beta v. The minus sign is coming from the minus sign right here that came from the cyclic rule. We can also transform this expression and rewrite it as partial v partial p equals minus kv, and because we have a reciprocal relationship for the partials, that can be transformed into partial p partial v equals -1 over kv. And so we can put partial. Actually, we don't need the reciprocal relationship yet, or in this part. We're actually only going to use this part, partial v partial p equals minus kv. And so that tells us that partial p partial t is beta over k. And so let's rewrite this dP, putting the beta over k right here. Now to transform partial p partial v, we go back where we were here, and we do use the reciprocal relationship of the partials to rewrite this as partial p partial v equals -1 over kv, and that allows us to write -1 over kv in place of partial P, partial V right here. So on the next blackboard, we're going to take this alternate form for the total differential of the pressure and integrate both sides of it to put it in a more useful form. Let's note that this should be minus 1 over kV right here. I had didn't have the V in there. So to set this up for integrating, we're going to assume that beta over K is constant, and we're going to need to move the V here over to here in with the or underneath the dV, so we can integrate that part. So let's set up the integrals, and let's note that we're going to integrate dt between T1 and T2, and the volume between V1 and V2. We're not going to specify a P1 and a P2 here. So we're going to perform the integration. We're just going to call this left side delta P, but it could be written as P2 minus P1. So when we integrate this first term on the right, we integrate dt and get T, and then we plug in the upper and lower limits, subtracting them by the fundamental theorem of calculus to get this. When we integrate the dV over V, we get ln of V, and so we're evaluating ln of V between V1 and V2. That gives us ln of V2 minus ln of V1, which is written more succinctly as ln of V2 over V1 using logarithm rules. So we wind up with this form for delta P right here, which turns out to be a more useful form for calculating pressure changes in terms of temperature and volume changes than this differential form. So that will conclude this video, and other videos that follow on Chapter 12 will be on specific examples or homework problems.